All right, welcome back, physics. Here is your next lesson on waves, and now we're going to be talking a little bit more about sound. One thing you should note is that there is a website link that I've posted in this material that I need you to go to and read through so that you have a little bit more information. Okay? That'll send you to the physics classroom website. All right, so today we're going to be talking about the intensity of sound. So what does intensity mean? First off, we need to figure out a little bit more about the energy of a wave. So we talked last time about what is a wave, that a wave is not the material itself. So right, we have this seal in water, right? The water isn't the wave, but the wave is the energy in it. Okay, so what part of a wave determines the amount of energy that it carries? All right, so that's what we want to figure out. And that is determined by the amplitude. So the higher the crest and the lower the trough, the more energy is being carried in that wave, right? If I have a tsunami that has a wave height that is hundreds of meters tall, that is because it carries a lot more energy, right, compared to little waves that you'll see when the ocean or the lake that you're at is very calm, right? There's not a lot of energy in those waves. They don't carry a lot of energy. Amplitude is simply the height, right? This is going to determine how bright our light is, how loud our sound is, the power of that electricity, things like that. So if you double the amplitude, you're going to double the amount of energy, right? When we were looking at when waves interfere, when one crest comes in and another, they double. They're twice as tall, which means that it has twice as much energy. So we just double the amount if we add two of the same together. All right, so intensity is a little bit different, right? Intensity, why wouldn't we just say energy of the wave if intensity tells us just the energy? So it must tell us something a little bit different. So the intensity of a wave is the amount of energy in the area of the wavefront over the amount of time. So the smaller the area, the more dense that energy is going to be, and the more intense that sound is going to be. Okay, so here you have the equation. Intensity, that capital I, is going to be the energy divided by the area multiplied by the time. If you remember back to our energy unit, you'll remember that energy over time is power. Right? If you have lights that aren't very powerful, they might emit a lot of energy over a long period of time, but they're not going to be very bright because they're not giving off a lot of photons per second. So it is energy over time, so we can simplify that to be power divided by area. So for our purposes, we'll be using the area of a sphere. When I speak, that sound doesn't come out in two dimensions or just one dimension. It comes out in the area of a sphere, not just a circle coming at you in a sphere. So the area equation we're going to be using is 4 pi r squared. So what does this mean, right? So you have this equation. Mathematics is really difficult for us to visualize, so it's helpful if we put some numbers here, we see how this works out in the real world. So if 10 million people are talking at the same time, let's say they're talking with the same volume that I have, with the same intensity that I have, they would produce enough sound energy equal only to the energy needed to light a common flashlight. So this is the population of New York, a little bit less, I think, and you would need all of them talking at once, and that would only be able to power a common flashlight. So it's not a lot of energy when we talk, but we hear each other relatively well. So that means that our ears are tuned to hear this sound very finely. We can pick up this small amount of energy with our ears. Okay, so how else can we understand this? So humans can hear sounds as small as 1 times 10 to the negative 12 watts per meter squared. So, right, it takes 10 million to power a light bulb, but our ears are so finely tuned that they can hear an incredibly small intensity. So you can hear things that are really, really quiet. So this is called the threshold of hearing, right? If a sound is smaller than that, it can't cross the threshold. It can't pass into what we can hear. So for comparison, a whisper is 100 times as loud as that threshold of hearing. So if I whispered in your ear, that is 100 times louder than you could, than the minimum amount of hearing that you have. All right, so let's think about the mathematics. So notice that our equation for intensity has an r squared underneath. This is a division sign. We've dealt with dividing by r squareds before. We did it with gravity. So this means that as the radius increases, the intensity is going to decrease by the square of that radius. So if I double my distance, right? The distance is the radius. So if I double my distance away, I will have only 1/4 the amount of intensity because I'm squaring that too. If I triple my distance, right? 3 squared gives me 9, 4 gives me 16. So when you're doubling that distance, you are dividing by the square of that distance, okay? So if I move twice as far away, how much did this intensity decrease? We said 4 times. Okay, so take a moment. I want you to do a little bit of practice. So a speaker outputs 0.5 watts of power to the air. If you stand 2 meters away, what is the intensity of the speaker at that distance? Okay, so take a moment, pause the video, try it out. What do you get? And then I'll put the answers in a separate spot on the assignment. Okay. All right. As well, so you finally got the tickets to the rock concert you've been waiting all year to go to. The concert speaker output is 282 watts of sound. How far away would you have to travel for the sound waves to be at the threshold of hearing? How far away do you need to be so that it is that quiet? Again, I'll put the answers in the material a little bit later. All right. So once you have finished those 2 practice problems, you should have an understanding of how to calculate the intensity of sound in particular. Okay. But that is it for intensity, and I'll see you next time.